So today we'll be presenting an algorithm in the graph theory for our project algorithm and design and analysis. और इस पेपर का जो नाम है वो है सिंगल सोर्स शॉर्टेस्ट पाथ विथ नेगेटिव रियल वेट्स इन बिगो ऑफ mn टू द पावर 8/9. मूविंग फॉरवर्ड, मोटिवेशन क्या थी ये पेपर और इस टॉपिक को बेसिकली लेने की? तो ऑफ कोर्स जैसे हमें पता है कि द रियल वर्ल्ड ग्राफ्स आर applicable in all of the domains, whether it includes finance, physics, computer networks, or especially in maths, right? So, but with that being said, graphs बहुत तरह के होते हैं, right? It can contain negative edge weights, like for instance, in currency arbitrage, a negative weight cycle can suggest a guaranteed profit, right? So हर तरह के ग्राफ्स होते हैं, जरूरी नहीं है कि सिर्फ पॉजिटिव वेटेड हो, नेगेटिव वेटेड, डायरेक्टेड और हर तरह के ग्राफ्स. So however, these graphs do come with a computational challenge, right? इसके लिए अलग अलग algorithms होते हैं, like the Dijkstra algorithm, but the problem with it is कि it fails when the edge weights are negative, right? Belbin-Buford जो है वो it works perfectly, but it runs in the time of big O of mn, and also it's not efficient when the graphs are large, right? So this research basically offers the first asymptotic improvement to the solution for graphs in which the graphs are in real negative weights. Moving forward, what's our problem statement? तो जो हमारा problem statement है वो है single source shortest path, right? In which we are given a directed graph with vertices v and edge, where the edge weights can be, of course, both positive and negative real numbers. Okay, और हमें करना क्या है? We need to compute the shortest path from a source to every vertex in the graph. So it's not like source to destination, but source to every vertex. Every vertex is our adjacent destination. So moving forward, what are the related work and limitations in our paper? तो ऑफ कोर्स प्रीवियस जो सॉल्यूशंस हैं, जैसे कि बेलमन-फोर्ड है, राइट? वो रियल इंटीजर्स को कैटर करता है, बट द रनिंग टाइम ऑफ इट इज mn, बिग ऑफ mn. इसी तरह से डाइजेक्स्ट्रा है, राइट? वो नेगेटिव, it's a much faster algorithm with big of m plus n log n, but it only works for non-negative integers, right? तो इसी तरह से, बट जो हमारा एल्गोरिथम है, it works in both real in real integers, और उसका जो रनिंग टाइम है वो इज अराउंड mn n to the power 8/9. तो सोल्यूशन इज बेसिकली, जो हमारी नॉवेल्टी है वो ये है कि इट वर्क्स on a randomized strategy where the main point is that it gradually eliminates the negative edge effects. So if we see it in the bigger picture, जो हमारा एल्गोरिथम है इस पेपर में जो बताया गया है, दे आर यूजिंग अ प्राइस फंक्शन. प्राइस फंक्शन क्या है वो हम आगे डिस्कस करेंगे, बट प्राइस फंक्शन करता क्या है? सो इट यूजेस द प्राइस फंक्शन व्हिच रीवेट्स द एजेस but without affecting the shortest path. So it identifies and eliminates the problematic nodes, which means जो जिससे हम कह सकते हैं कि they are called negative vertices. और ये किस तरह करता है? It does through a clever reduction, जो हम आगे डिस्कस करेंगे किस तरह से करता है. और once all the negative vertices are removed, then what it does is it runs the Dijkstra algorithm, और फिर ये एक shortest path निकालता है. Algorithm का overview, I'll walk you through the step by step of our algorithm. So our algorithm is basically is a collective of 4 algorithms. तो ये basically अलग 4 algorithm जिसको मिला के एक algorithm बना है. So it basically has 4 key stages. The first one is the betweenness reduction. So in this algorithm, in this subsection of the algorithm, it uses randomized reweighting, as I said before, to reduce to reduce the number of how many vertices lie between other in many paths. So होता क्या है इससे कि it makes the graph more structured and easier to manage in the later steps. फिर तो दूसरा जो हमारा सब पार्ट है एल्गोरिथम का, it's named as negative sandwich or independent set, where what it does is it searches for negative sandwich. Negative sandwich का क्या मतलब है? So basically it means कि it's a cluster of negative edges. Negative edges जैसे मैंने बताया कि जिसका जो वेट है वो नेगेटिव या तो पॉजिटिव वेट होता है, और ये नेगेटिव वेट होता है. अच्छा, नेगेटिव और पॉजिटिव को हम इस तरह से एक सिंपल आसान लफ्ज में इस तरह समझ सकते हैं, जैसे इफ यू वांट टू गो फ्रॉम अ सिटी टू अनदर सिटी, राइट? तो बीच में रोड्स होते हैं, राइट? और रोड्स पे टोल्स होते हैं. अगर आप टोल्स अज्यूम कि देयर आर टोल्स, राइट, on the road, so those tolls are positive edges. but अगर मैं आपको कहूं कि अगर आप वो वाला रास्ता लेंगे तो मैं आपको कैशबैक दूंगा, so तो उल्टा आपको देने के बजाय आपको पैसे मिलेंगे, so that's negative edges for them. So in the negative sandwich edge, what it does is that it removes it searches for the cluster, right? or what it helps is that it helps to isolate the problematic regions in the graph. Then what it does is there's a second price function which पहले ऊपर भी एक प्राइस फंक्शन था जो वर्टिसेस को रिवेट्स करता था. then this is the second price function which reweights the graph, to make the remaining edges removed, right? And the last section of our algorithm is the hop reduction. This algorithm restricts how many edges can appear in a path using hop limited shortest path, or once in this part enough vertices are removed, as I said, then the digest algorithm is applied. So price functions, I would say, assigns a value to each vertex, right? और ये basically ये formula है which is w of u comma v is equals to the weight of that specific edge, right, plus phi of u यानी वो जिस source से हम जा रहे हैं minus phi of v यानी जिस vertex पे हम जिससे निकल रहे हैं और जिस पे जा रहे हैं. So what it does is that it preserves, it reweights the vertices but it preserves the shortest path. तो पेपर में बताया गया था कि it was borrowed from another algorithm which is the Johnson algorithm, और it is used to eliminate the negative edges. So ये बहुत एक heart of the algorithm है जो price function बहुत इस algorithm में हमने use किया है. Okay.
So now moving on, तो हमारे पास second part of the algorithm is gradually eliminating the negative edges. So initially what happens in this algorithm is that first we identify the negative vertices, basically those nodes with the outgoing negative edges. And then using the price functions that Hussein mentioned earlier, we will reweight the graph to remove their negative influence, like maybe decreasing their weights and making them a near to positive or making them more negative. So after each round of reweighting, then we eliminate some negative vertices. And most importantly, that the edges that start off non-negative also remain the same throughout, like which are non-negative, all the positive ones remain positive throughout this reweighting of the edges. So now moving on to the third algorithm, the third step you could say. So here, if we find one hop independent set, which is basically negative vertices without directive negative connections, so those can be eliminated by using the Johnson algorithm, as mentioned by Hussein earlier. And otherwise, we look for a negative sandwich. What negative sandwich is? It is a clustered negative edges. So if we find one, a group of vertices, if we find one sandwich, then we reweigh to make it R remote. Remote here in this case means that its effect is limited to a small part of the graph, meaning that it only affects small number of the vertices in the graph. So this is how the negative sandwich and the independent set of that particular part of the algorithm works. Lastly, so here all the approaches basically are quite similar and interlinked. So here also we apply a second price function to the graph, and here also the goal is to make the negative edges within our found negative sandwich R remote. And then we employ the hop limited shortest path, and which basically means that allowing a limited number of negative edges per path. So this involves like alternating between a round of Bellman-Ford on negative edges and Dijkstra's algorithm on the rest. So once all the hop limited shortest paths are approached, then the graph is passed through the Dijkstra algorithm to compute the shortest path. And all the final distances then are adjusted based on the applied price functions. And then the algorithm, the final algorithm can also detect the negative weight cycles. So this was the complete overview of our algorithm. The time complexity of this whole algorithm is big O of m into times n to the power 8 over 9. And the complexity that was improved, which is basically n to the power of 8 upon 9. That improvement particularly came from reducing the number of negative edges and the reapplying of the weights and the hop limited steps. And particularly, if I may say, that improvement came from the repeated elimination of a to the power 1 upon 3 negative vertices using the subsets that were independent or sandwich. And then moving on to the space complexity of this algorithm is O of m plus n, where m is the number of edges and n is the number of vertices. So complexity is justified by the data structures that store the graph, the two price functions, and the data structures that are used for the hop limited searches. Now, how we tested out our algorithm. So for the data, we randomly generated graphs of varying sizes, particularly of vertices having around 200, 500, 300 nodes. And for the implementation, we used Python, and the code included Bellman-Ford and the particular randomized algorithm that we have been discussing throughout. For the evaluation, we used the runtime of the code compared with the Bellman and the optimized algorithm. So the time taken was the R metric for this setup. Now for the results, we computed the times that both algorithms took on different number of vertices. So as you can see that we tested out on vertices around 10 till 50, and we can see that Bellman-Ford considerably took more time than the randomized algorithm, and the time that Bellman-Ford took in 50 nodes were in 50 vertices were around 80 milliseconds, while the optimized algorithm took around 100 milliseconds, 10 milliseconds, sorry, my bad. Now, first I'll discuss the code and then we'll move to the final work, which is the limitations and the future discussions. So let's discuss the code here. So firstly, in the code, we have um, programmed the Bellman-Ford algorithm, which is the classic algorithm. So it basically works by initializing the distances to infinity, if you can see, and then it except the source, obviously, source is set to 0, all the rest are set to infinity. And then it repeatedly relaxes the edges, which means it updates the shortest path for n minus times. And after the main loop, it checks that if there's any negative fade cycle. And the output that it returns is that the shortest path distances or none if the negative cycle is detected. Then in our algorithm, we implemented the randomized algorithm, which is a simplified version. It calculates the shortest path using the hop limited version of Bellman-Ford, where only a fixed number of edges are allowed. So, like Bellman-Ford, it limits the number of hops considered in each path. Number of hops are negative edges, and it runs for max hop iterations instead of the full n minus 1 iterations. And it also returns the shortest path distances with hop limited edges. Then our third function is eliminate negative edges, which randomly eliminates negative edges from the graph to simplify it. It takes a list of negative edges from the graph, it then removes the k negative edges, and if there are no negative edges, it simply returns an empty list. Then lastly, we have our main function that combines the hop limited and the negative edge elimination, and it calls the hop limited function to compute the shortest path and then identifies all negative edges and removes some of them. One thing I forgot to mention earlier is that this is a partial implementation of our algorithm that is discussed in the paper. Because when we were implementing the full algorithm, the time complexity was not that we were getting was not as expected. So we implemented it partially as we used only two steps. The first was the negative eliminating negative edges. The second one was the hop limited approach. So
I
this
mean,
approach gave us
it is possible that the code which we were implementing for all the four algorithms, maybe that's not accurate. So that's why the time complexity was worse than the Bellman-Ford. So what we tried to do is we tried to implement it individually. And when we did the first two algorithms, so we found that the algorithm was performing well than Bellman-Ford. So that's why we did the partial implementation for now.
Yeah. So lastly, this function basically compares the running time for both the algorithms. Now I can run the code simply. One thing I forgot to mention that we tested out on these number of this and vertices. So here, as you can see, vertices are 10 to 50, edges are 20 to 100, and these are the results that we get. So now getting back to our presentation. So for the limitation and future work, the major limitation or struggle of our algorithm, we could say, is that it doesn't perform really well when there is high density of negative edges. So that particular overhead, that particular elimination causes the algorithm to fail, particularly against the Bellman-Ford, and Bellman-Ford performs better in that case. And in the large graphs, also it has a certain inefficiency. So that's our algorithm struggling that for the future work, as we discussed earlier, that we'll be implementing the full algorithm so that the desired time complexity is achieved and we could improve on the components like the price function debating and the elimination that we skipped for this time. So now to conclude, this randomized algorithm offers the fastest solution for single source shortest path problems on graphs with negative weighted edges. The algorithm reduces the time complexity from O of mn to mn 8 over 9. And lastly, provide a significant speed up in graphs with negative edges, making it a strong choice for large scale and real world problems like currency arbitrage and network optimization. So this is a paper that we reference to. Thank you.